To keep an industrial press from tearing itself apart under thousands of tons of force, the system needs to know exactly what's happening at impact. But there is a strict language barrier. The physical world operates in variables like temperature, pressure, flow, and speed. Electronic control systems, however, only understand voltage and current. This diagram shows the first step, the sensor. It detects physical changes, like heat or pressure, and outputs a non-electrical physical response. But routing that raw output to a processor fails. Digital processors cannot read mechanical shifts or thermal expansions. Detecting a physical change is only half the problem. Without a translation layer, raw sensor data is invisible to an automated system. We insert a signal conditioning unit, or SCU, converting the non-electrical physical output into a measurable electrical waveform. Standard SCUs include ADCs, amplifiers, filters, rectifiers, and modulators. Combining these two components, the sensing element and the SCU, creates a transducer. This operates entirely on the principle of transduction, taking energy in one raw form and converting it into another to extract readable data. The principle applies everywhere. A microphone turns sound into voltage, and a loudspeaker reverses the process. Every transducer relies on this exact measurement pipeline. To see exactly how physical mechanics are converted into voltage, we will deconstruct two highly specific industrial transducers, one thermal and one spatial. The resistance temperature detector, or RTD, is a passive thermal sensor. It works because pure metals change their electrical resistance in a highly predictable way as they heat up or cool down. This cross-sectional diagram displays a standard RTD assembly. The core sensing element is a pure platinum resistance coil, whose resistance increases linearly as temperature rises. Protected by a hollow ceramic former and cement, it routes data out via electrical leads to an external terminal. The platinum coil perfectly fulfills the role of a sensor by changing its physical resistance in response to heat. But physical resistance itself is not a readable voltage signal. Wired into one arm of a Wheatstone bridge, the passive RTD receives a constant current to generate a measurable voltage drop. As temperature varies, resistance shifts, unbalancing the bridge. Comparing this current resistance to a 0-degree baseline outputs a precisely calibrated temperature reading. This high precision comes with operational trade-offs. The reliance on pure platinum makes RTDs significantly more expensive than alternatives like standard thermocouples. Because the unit tracks tiny fractions of resistance, even minor corrosion or a slightly loose wire connection will introduce massive data errors. An RTD illustrates the transducer pipeline precisely, a passive physical material made useful only by a highly sensitive, mathematically balanced external circuit. To measure spatial linear displacement rather than temperature, engineers use a completely different mechanism, the linear variable differential transformer, or LVDT. This cross-sectional schematic reveals the LVDT's layout: 3 coils wrapped around a cylindrical former. The primary winding, labeled P, sits dead center. 2 secondary windings, S1 and S2, flank the primary, wired strictly in series opposition. A movable hydrogen-annealed nickel-iron core slides inside. Hydrogen annealing is a mandatory manufacturing step for this core. It eliminates harmonics and residual voltage, ensuring the transducer maintains a high signal-to-noise ratio. Unlike the RTD, which alters its own material structure, the LVDT relies on its physical geometry. The fixed layout dictates exactly how magnetic flux will behave when the core moves. In the baseline state, an alternating current drives the primary coil. When perfectly centered, it provides equal magnetic coupling to both secondaries. Wired in series opposition, voltage S1 equals negative S2, canceling out for an output of 0. If the core slides upward, the magnetic coupling shifts. Flux lines concentrate toward the top coil, making S1 greater than S2, generating a non-zero output voltage. Conversely, as the core slides downward, flux concentrates toward the bottom coil. S2 is now greater than S1, generating a non-zero output voltage exactly 180 degrees out of phase. Because the core floats magnetically inside the cylinder without making physical contact, there is zero friction, giving the LVDT an almost infinite service life. It is physically robust under extreme conditions. operating reliably from -265 degrees Celsius up to 600 degrees without permanent damage, even if mechanically pushed past its design limits. Its response time is virtually instantaneous, strictly limited only by the physical inertia of the iron core itself. The LVDT is an elegant piece of engineering. It integrates the sensing movement of the core and the conditioning unit of the opposing secondary coils into a single mechanical housing. Despite robust designs, transducers are incredibly precise instruments. When deployed into the field, they become highly susceptible to environmental interference. This split-screen image demonstrates the absolute necessity of continuous calibration against known standards. Notice how the uncalibrated waveform slowly drifts from the baseline over time, while the right side shows a tightly aligned signal, actively calibrated under actual test conditions. Operators must continuously monitor the ambient environment, actively correcting the data output the moment humidity or ambient temperature shifts unexpectedly. Often, engineers deploy artificial environmental controls, enclosing the transducers in heavy, temperature-controlled housings specifically to isolate the sensitive mechanisms from external shocks and vibrations. The integrity of the data pipeline depends on a continuous commitment to controlling the surrounding environment, far beyond the initial physical installation. In offshore industries, heavy-duty LVDTs are deployed into harsh environments. They measure the immense physical forces acting against the rig's underwater structural supports. They also function as secondary transducers, monitoring precise structural movements of massive vessels like the Slovenia during critical maintenance operations. Inside power generation facilities, networks of RTDs and LVDTs work continuously, monitoring critical components deep inside massive generators like these Parsons turbines. Whether measuring through platinum resistance or magnetic induction, these devices allow control systems to react to physical forces in real time, the specific capability that makes automated industrial safety possible.